Good morning to you all. My name is Liliana Teixeira. Right here, thanks. I'm from the University of Twente, and I'm also a co-scientific lead of the Organ-on-Chip Center of Twente. So today I'm going to give you an overview of how we can be inspired by physiology, actually pathophysiology as well, to create more organized or more structured, more mimicking organs on chips. So this slide is a bit redundant here, but what I wanted to call your attention for is that we should understand and really mimic human pathophysiology and take the cues that are given by nature to instruct cells to do their best, to behave in the way that we want them to behave, to have our models more and more effective. And with that, we can also make them more translatable and more personalized. And at the end, what we want is to have pathologic specific models. And also, basically, we want to target drug development. That's one of our main goals. And for that, I'm going to talk about 3 case studies today. And the idea is to show you how we can play with architecture of instructive elements, as well as geometries, and as well as how we can put tissues together to add complexity to organ systems. So the first case I wanted to show you today is about a lung-on-chip model, actually an alveoli on a chip model. And here we added complexity by adding 3D instructive elements to the chip model. So what we wanted to do here was not to have a flat membrane, but to recreate really the alveolar structure, the 3D environment that the cells are exposed to. And the reason for that was that we noticed that curvature plays a really important role in how the cells that are present in the native tissue, how they mature, how they behave. So it's really important to take into account which cell sources we use, of course, but it's also equally important to steer them to mature properly and to have the diversity of phenotypes that we want to have at the end to again have a more effective model. And what we did was to look at the alveolar structure and really flatten down these structures and recreate these, let's say, 2.5D or or hemispheres that we have in the native tissue. And for that, we used a membrane, okay? We used a thermoform membrane that is also porous, that really recreates these structures we wanted to mimic, also regarding to the size. And that membrane was also very easily incorporated into an on-chip system, as you can see here. So we addressed also the perfusion to guarantee that the flow would not affect the cell seeding. And all the cells were uniformly distributed throughout these kind of membranal structures. So with this, we recreated a, let's say, 2.5D or 3D, as we can call it. And we seeded primary cells, human primary cells. And again, what we wanted to see was that whether we could mature these cells to the different phenotypes we wanted. So we wanted alveolar type 1 cells as well as type 2. And we also assessed for the epithelial markers. So we saw that these cells behave differently depending on the curvature that they were exposed to. So at the bottom, the cells were having different phenotypes than more at the edges where the curvature is a bit more sharp. And not only we seeded primary cells, alveolar cells, we also seeded endothelial cells, so from the microvasculature, and they could be equally nicely seeded on the other side of the membrane. And with this, we recreated a more 3D instructive organ-on-chip alveolar model. So moving on to the next case study. In this example, I'm going to emphasize on how the geometry can also play an instructive model. And again, here it's really looking at the question you want to address. So the model I'm going to talk about, okay, is a colon, cancer colon model. Cancer model on the colon, actually. And what we wanted to address here is how the drugs penetrate into a solid tumor. So colon cancer was an example of a solid tumor. It can be extrapolated to many other solid tumors, of course. And the idea was to see how a nanoparticle would diffuse inwards. And the idea was to recreate a window into a tumor, like we would cut halfway and see the penetration of these nanoparticles. So what you can see here is the colon cancer cells in the middle chamber, where we see them in a 3D matrix. Here, the idea was also to start with a simple 3D matrix, but the point was to have more instructive elements here as well. And this matrix can be stiffened to recreate more and more the natural environment, so the pathophysiology again, and how this cancer microenvironment progresses throughout time. So the matrix can be stiffened on demand. So here, as I mentioned, the cancer cells are in the middle, and in the surrounding channels, we have microvasculature. And what we wanted to see was how we could achieve controlled gradients of drug-loaded nanoparticles. So we chose a standard drug to treat colon cancer, just to assess how this drug would diffuse inwards. And here we can also play with the size of the chip. So this was relatively small, but you can also control these kind of parameters quite easily and assess the diffusion of these particles inwards, and as well as the specificity into the tumor cells, to attach to the tumor cells, and how the viability of the cells are affected by these drugs. So we wanted to also check if these drugs, so these nanoparticle loaded drugs, would affect only cancer cells or also vascular cells. So I'm not showing this work here today, but it has been published already. Okay, moving on. What I want to do now is to move on to the next case study. So far what you saw was that we can quite nicely control the environment of the cell. So you can see these approaches as creating a house for the cells and instructing them the best way as we can. But when it comes to complex diseases, one house or that hosts a couple of cell types the best we can is not sufficient. And for complex diseases such as, let's say, osteoarthritis, we need to go a step further and create a neighborhood of houses that permits the steering of cell differentiation and communication between tissues. So I'm going to talk about how the idea of the development of joint on chip came to be, and the idea of this coupling of different tissues to form a joint environment was to focus on creating a model towards osteoarthritis. And osteoarthritis affects a huge amount of people worldwide. So basically 1 in 10 people are affected. So we will not most likely die of it, but we will be highly disabled in terms of mobility. So the incidence is quite severe, as well as the damage that it causes in the society. And this disease, in spite of its incidence, has an unknown trigger, so we don't really know how to treat it. And the causes might be in one of the different tissues or in the different, or affecting a couple of tissues altogether. So the idea here was to couple these tissues in joint on chip model. So taking, for example, the osteochondral unit, the synovial unit, the fat pad, and putting all these tissues together to recreate the joint, and also add mechanical stress to simulate, for example, movement or harsh movements that would aggravate the disease progression. So what you can see here was the first step, was the model created to reproduce osteochondral unit. And what you can see here is a model that already has the actuation system that simulates the movement that the articular cartilage is exposed to, as well as the bone. So this movement is not one impact, let's say, it's more of a wave movement, and the cells feel it differently. So that's what we showed in this paper here. I'm just going to give you a glimpse of it. But basically, what we see is that this kind of wave-forming compression or mechanical actuation really steers cell behavior, and the cells are quite affected by this kind of steering or input. And you can see this in pro-inflammatory factors. So cytokine release profiles were analyzed by SPRI, and you can see already quite a striking difference in the wave movements on the actuation in these different compartments that enables this wave-like compression. We also looked at how the matrix was being affected, how the matrix deposition was being deposited as well as remodeled. And we also saw quite striking differences in the collagen type 2, which is specific for cartilage, in this kind of wave-like actuation movement. But as I mentioned before, joint is not composed only by one tissue. So what we did afterwards to look at how we could recreate another tissue that plays an important role on disease progression on osteoarthritis. And that organ was the synovium, so a synovial membrane. And here what we did was to recreate this type of membrane and the shear stress that it's exposed to. So it's more recreating the hydrostatic pressure of the fluid that is in the intra-articular space. But what we could see here is that this is fundamental to recreate the pro-inflammatory profile that is typically in the native tissues and in the progression of the disease. So now I wanted to also do some shameless advertisement to the Organ on Chip Center. And taking into account what I mentioned before, yeah, it's important to recreate the housing system for the cells, as well as the neighborhood for the cells, but also what matters is the community that we create in the development of organs on chips. So in this center, we want to connect researchers, we want to connect different skills, different expertise in all steps of developing the chips, so from design to validation. And we have that expertise in-house to give input to this kind of providing this kind of complexity to the systems, and also recreating the best we can the pathological cues. And also one of the main keys of the center is not only connect researchers, but also connect chips. So I'm just giving you an overview of the work that is going to be presented later on by Andries. Basically, what we want to do is create complexity, but in an easy way that we can also enable standardization and automated control. So the idea here is to create a plug and play system where we can connect these chips in an easy way. So just enable the connection of different designs and also enable different readouts in an easier and more facile way that we can all understand and work with. So just to bring the whole story together, yes, we need to balance complexity, but we also need to keep in mind that we shouldn't make our lives difficult. So what I showed you here was that we can easily implement these kind of cues that steer cell behavior in an easy way. So these instructive elements are easy to add to the chips. We just need to ask a specific question to justify this addition of complexity. So again, the models need to be designed to fulfill specific applications, and we do need to understand the limitations of the models to make them efficient. And the technologies developed that can be directed to enable easy translation and validation of the models. So as we heard already quite a lot until now, we need to guarantee the acceptance of these models by the regulatory entities. And what's the main goal here is walking towards animal reduction. So yes, we talked about animal replacement, but I think at this stage we can contribute already quite a lot for the reduction of the animal use. And well, this was what I wanted to show you here today. Just a word of thank you to the people that contribute for being here, as well as to the people who conducted the research, so the PhD students involved. And if you have questions, I'll be happy to answer them. Thank you so much.
We have time for questions. Please come up to the mic.
Henry from University of Pittsburgh. Thank you for the great talk. So for the synovial or chip model, so what kind of cell did you include in that chip?
So we used to sit on top of, let's say, the membrane were synovial fibroblasts, primary human synovial fibroblasts.
Okay, thank you.
Hi, that was a very interesting talk. I just had one question. I noticed several of your slides mentioned actuation. I wanted to know if that's basically driven by the shape of the membrane, or is it more actively actuated?
Yeah, so it's a good question because it might not be really clear there. So I can explain a little bit more on that. It's not the typical membrane that you'd see on the chips. So in that way, it's a vertical membrane that gets actuated in a sequential way. So basically you push the gel that is in the center chamber downwards in a sequential manner, simulating the bodily the movements of the joint. Yeah. So it's a PDMS-based membrane.
Hi, Frank Baroli, Humane Society. Thank you for your talk. I'm wondering, with the AT1, AT2 lung cells, did you see any evidence for formation of tight junctions in your curved cultures or any other cell-cell interactions?
Yes, absolutely. So what you saw here was just one example of one cell type we used, but this has been shown or we published before using different cell types. So the different cell lines that are typically used, such as KLO3. And yes, we saw very different ways of the cells being connected and forming this kind of uniform covering of the membrane, depending on the cell type. And the best one that we saw in terms of behavior of making this uniform spreading and connection was with the primary alveolar cells. Yes. Yes, it's very nice already. Within a couple of days, the cells do spread independently or where they are in the curvature. Yeah.
Hi, thank you so much for the talk. I was wondering if you had done any characterization of surfactant production in the lung epithelial model that you had generated.
No, that's a good point and absolutely needed, but for future work. No, it was not done as of yet. So this is quite recent work, so it was just published and it's just opening doors for next questions and we can definitely address that. Yeah, thank you.
Any other questions? I have a question. In the deformation of the system, do you see maintenance of the tight junctions after you deform the cells and then it comes back? Or do you see a gradual destruction of the tight junctions with time?
So that's also a very important question. Thank you for asking. So what you saw here was a membrane that is not elastic. So it's based on polycarbonates. And here you don't see the cells being affected at all because they are just in a stiff-like environment. So the idea was to start with giving the instructive element as geometry. Later on, it was done also with an elastic polymer. And there you already see that the cells, it disrupts because the environment is quite dynamic. So that was not an ideal system. So there again, you have to look at the limitations of the system and how much you can expand and give this kind of elastic movement on these membranes. So that's one limitation that we faced with using elastomers. Yeah.
Okay.
I guess I have a question about the lung model. You mentioned the curvature matters in terms of for the model. I'm wondering, have you looked into what scale of the curvature would matter, like in size of 100 micron, 10 micron? Just wondering.
So we looked at how the alveolar structure was and replicated that kind of blindly, assuming that if nature did it so, that would be a good starting point. But a lot of work has been done to see the influence of the different cell types in curvature in different levels or ranges of curvature. And the cells are affected by it. Different cells affected more, some cells affected more than others, but it has been published by others, not specifically in this work. It has been done with the right range of different morphology geometries, even not only in this kind of hemispheres, but also in tubular shape and membranes. Yeah.
Any other questions? I have a couple minutes. We want to try and stay on time because this is being live video cast, and so we don't want to get off of time. Have you looked at trying to interconnect the different systems?
Yes, so now we have two systems that we know that work. And basically we connect them via the intra-articular-like system, and we do that via tubing. So that is working quite okay. I think the complexity will be added when we start adding more and more tissues. As I mentioned, the next one in line will be the fat. So simulating the Hoffa's fat bed. And that will create some questions that we need to address in terms of compatibility with the media, and also at which stage we need to connect the chips. So in which stage of maturation will also play a critical role there. So they can be connected, but we need to address all these challenges in terms of timing and connectivity in terms of medium performance and enabling the cells the best environment they need to. Yeah.
Okay. Vijay?
Yeah, really quickly, Jorge Mojica, Santiago, University of Florida. I wanted to ask you about the joint-on-chip platform that you're developing in terms of the dynamic studies that you're doing at mechanical simulation. Have you looked at fatigue or multiple sequences and the dosing of the actual stimulation that you're applying in your cells?
Yes. So what we looked at was basically looking at physiological loading as well as pathological loading. And we assumed that when cells started to die, basically when it was affecting cell viability and increasing dramatically the pro-inflammatory factors. So yes, you can have a wide range, and our limit was when it was affecting viability. So you can have these ranges quite well controlled in simulating just normal loading, exercise, pathophysiological loading regimens that would really aggravate the disease further. Yeah.
All right, one last question, Wesley.
So in the clinic, there's a lot of work trying to regrow cartilage, especially. Does your chip, can it model this at all?
Growing cartilage?
Yeah, regrowing or, just kind of.
So what we do is use already cells. So we use chondrocytes to start with. So we do not differentiate same mesenchymal stromal cells into chondrogenic lineage. But the cells do behave quite well depending on the matrix that you put them in as well. So you need to let the system mature, and this takes basically 2 weeks, so 10 days to 14 days with differentiation medium, to be sure that the cells already produce a sufficient pericellular matrix that will enable them to feel these forces that we are exposing them to. And in that way, we can also see the remodeling of the matrix later on as an effect of these pro-inflammatory responses.
Thank you.